At its heart, chemistry is the study of matter, a substance's properties, how it's made, and how it interacts with other substances. The overall theme of this course is a survey of the elements as organized by the periodic table. And since each element's properties and reactivity are dictated by its atomic structure, we have to start by talking about atoms and atomic theory. Human beings are inherently curious, and we've been looking for ways to explain the world around us for as long as we've existed. One early theory, popular in ancient Greece, suggested that all matter consisted of 4 elements: earth, fire, air, and water. Gold, for example, is a shiny solid, so it was said to be a mixture of fire and earth. Fire because it's shiny, and earth because it's solid. I imagine many of you have heard the term firewater as a reference to alcohol. Water because it's liquid, and fire because it burns going down. This theory was commonly accepted at the time when Democritus proposed the first part of modern atomic theory, almost 2,500 years ago. He suggested that gold cannot be divided into fire and earth, but that if you cut a piece of gold in half, it was still 2 pieces of gold. And if you cut them in half, it's still gold, and so on and so forth as you keep cutting until you reach a point where you can't cut anymore. At that point, you have reached the point of no more cuts, atomos, the thing that cannot be cut, or, in modern terms, the atom, the smallest piece of any element. The next key component of modern atomic theory came over 2,000 years later when Antoine Lavoisier proposed that mass could be neither created nor destroyed. To fully appreciate how revolutionary that concept was at the time, put yourselves in the shoes of the people living back then. They had no way of knowing about substances they could neither see, hear, smell, taste, nor feel. If you go camping and put logs in a fire pit, the ashes left after burning the wood don't have the same mass as the logs you started with. So if you didn't know that water vapor and carbon dioxide evaporated, how could you possibly conclude that mass was conserved? Instead, there was a theory that wood had a life force called phlogiston. And that life force was lost through the burning, and that's why the mass was lost. Of course, the same phlogiston theory was also used to explain why iron gained mass when it rusted. So a better theory was needed. It took an experiment by Joseph Priestley to provide the necessary evidence. He took mercury and oxygen in a sealed container, weighed it before and after reaction, showing that the total mass stayed the same. Then he took the resulting mercury oxide and heated it to break it back down, showing that a gas was produced, providing the evidence that it was able to relight a smoldering splint. And that was the original proof that oxygen gas existed. And based on that work, Lavoisier developed the more generally applicable law of conservation of mass. The third key component of modern atomic theory was added about 10 years later by Joseph Proust, who proposed the law of constant composition, or what I like to call the law of water is water is water. All water, no matter where it comes from, consists of the same ratio of hydrogen to oxygen. We know today that it's 2 atoms of hydrogen for every 1 atom of oxygen. In those days, they had mass proportions instead, but it was the same general idea. Put those 3 pieces together, and you're John Dalton, and you've just developed the modern atomic theory of matter. His theory actually holds pretty well today, which is pretty good considering that it's 200 years later. But of course, as you read through these points, you'll probably notice that there are a few that sound not quite perfect to you. At this point, if we were in a live class, I would be stopping and asking you to think about how you would refine this atomic theory of matter to include discoveries that have been made in the last 200 years. Since we're doing this by video instead, what I'm going to ask you to do is pause the video and think about how you would refine this theory. And once you've got an idea or 2, then you can unpause and see what other students frequently come up with. And now that we're back, let's think about what sort of ideas often come up in this discussion. The first point that often sounds a little off to some of the students is this idea that all matter consists of solid and indivisible atoms. Of course, not all matter is solid. Some of it's gas and liquid, but also It's pretty common for somebody to remember that there are in fact species smaller than atoms. We are all familiar with protons, neutrons, and electrons, and if we take enough physics, we may also be familiar with even smaller particles like quarks. So atoms are not actually indivisible. It's just that once you get below the atomic level, you're not dealing with the same element anymore. So we have subatomic particles. The next point that can oftentimes be mentioned is that not every reaction ever maintains the identity of every element. There is a special class of reactions called nuclear reactions in which one element can decay to a different element, or alternatively, we can combine two atoms of smaller elements to make one atom of a larger element. So the identity of atoms is preserved in all normal, typical chemical reactions, but not in nuclear reactions. And that would have to be added as a caveat to point 2 in this atomic theory. Except nuclear reactions. And then the third point that gets raised relates to both the third and fourth bullet points in this list here, and that is the existence of isotopes. Not every atom of carbon has the exact same mass. There are atoms of carbon that have a mass of 12, some that have a mass of 13, and some that have a mass of 14 atomic mass units. And so mass is not actually the defining property of an element, as we'll see later. Number of protons is. Similarly, we can have isotopes of different elements that, if you round to a small enough number of digits, appear to have the same mass. If you measure the masses accurately enough to enough decimal places, they will differ. But if you're talking whole numbers, there are certainly cases where there is both an oxygen 18 and another element that has an isotope with a mass of 18, for example. All that said, we didn't do an enormous amount of refinement to this theory. The bare bones of this theory are really good and hold true. And the first several topics that we added as edits are going to be the first several topics that we talk about in Chem 1000.